Oi lads, it's Danny here today, bringing you a lovely video. In today's video, we're going to take a look at infinity to the power of 0. What's that equal to? Let's get right into it then. So what you are going to have to do straight away is we're going to use calculus we're going to use calculus 1 more precisely. We're going to use limits. And we are going to represent infinity to the power of 0 as the limit as x approaches infinity of some f of x function. And the f of x function we need to select is an f of x function as x approaches infinity will tend to infinity. And likewise, we have a g of x function, which we need it to tend to 0 as x approaches infinity, so we can represent infinity to the power of 0. So let's choose our f of x and g of x function. For the sake of this example, I will choose my f of x function to be x, and x tends to infinity as x approaches infinity. The best way you can look at it is when you look at a y is equal to x line. As the x gets larger, your y variable gets larger. So if it's x going to tend to infinity, the y variable is going to tend to infinity as well. And in the exponent, we have 1 divided by x. And 1 divided by x, or 1 divided by some very large number, is going to yield an answer of 0. So that's going to tend to 0. So this is a perfect representation of infinity to the power of 0. Right, so let's solve this limit. So we got two sides of this limit. We got the y side and we got the right hand side. The left hand side is the limit as x approaches infinity of y is equal to the right hand side, which is the limit as x approaches infinity x to the power of 1 divided by x. We basically apply the limit on both sides of this equation. We are going to start solving on the right hand side. It's very straightforward. We are going to use the laws of logarithmics. So when you have an exponent and applying the laws of logarithmics, we can rewrite it as ln of x, right? And we got the divided by x section, which is very important because it's going to be, we're going to move it instead of an exponent as a multiplication using the laws of logarithmics. Very important. So once you have written it in this stage, we are then going to look at the right hand side more in depth basically, and we're going to take the limit as x approaches infinity. So we're going to apply infinity in the numerator and denominator respectively, and what you are going to notice is you got a very indeterminate form right here. Infinity divided by infinity is basically indeterminate, and there's actually a way we can solve this and we can actually get an answer from it, and that's by using L'Hospital's rule. We're going to take this limit and we're going to apply L'Hospital's, and L'Hospital basically states is that if you end up with an indeterminate form in the first part, when you try solving the first time around, right, you can basically take a derivative in the numerator and denominator, and by doing so, you can basically, instead of receiving an indeterminate answer, it could give you an answer basically. And the way we do it is just applying the derivative, like I said, and in the numerator, you're going to just have 1 divided by x divided by 1 in the denominator, and notice you can basically write this as 1 divided by x, and when you apply the limit as x approaches infinity of 1 divided by x, you are going to end up in an answer of 0. So we did not get an indeterminate, we got actually a 0, we got a finite number. Very important. Right, so we are going to basically replace this 0 inside this equation over here. So we're going to have limit as x approaches to infinity of ln of y is equal to 0. We are going to basically apply natural Euler's number on both sides of this equation, right? And that's going to eliminate the ln. So we're trying to basically solve for the limit as x approaches to infinity of y, and Euler's number to the power of 0 is just going to be equal to 1, and we are going to basically, limit as x approaches infinity of y is basically equivalent of me saying limit as x approaches infinity of x to the power of 1 divided by x. So we established that this is 1, so therefore this has to be 1 by default. So we have basically proved that it's equal to 1, but we're not done yet. We need to try a different example. And what you are going to notice when we try a different example, right, let's try e to the power of x to the power of 1 divided by x instead. E to the power of x, as x approaches infinity, will tend to infinity, right? So let's see what this answer yields, right? Very important. So this here is our limit, right? We are basically going to cancel the x terms out. We got an x in the numerator and denominator, and what we're left with is the limit as x approaches infinity of e to the power of 1. And this answer here yields an answer of e. It doesn't yield an answer of 1. Therefore, we got one set of functions that equals e, and one set of functions that's equal to 1. And by default, so as a result, infinity to the power of 0 is basically inconclusive. It's indeterminate because you got two different answers using two sets of different functions, all representing infinity to the power of 0. So therefore, infinity to the power of 0 is basically indeterminate. So if you enjoyed this video, please leave a like and subscribe, and I'll see you later.